Good day everyone. I am Kimberly Tambiga from Business Science 2. So today we're going to tackle about meteorology. I hope to share with you the significance of this field and its impact on our daily lives. So first, let's start with the definition of meteorology. What is meteorology? Meteorology is the scientific study of the atmosphere and its phenomena, including weather and climate. It involves understanding the processes and interactions within the atmosphere, predicting weather patterns, and analyzing climate trends. In simple definition, meteorology is the study of the atmosphere, weather, and climate. So we have the Greek word of the meteorology. The word meteorology comes from the Greek word meteoros, which means high up, and logia, the study of. Therefore, the word means the study of things high up or in the sky. Meteorology is the study of things in the sky, including clouds, rain, snow, temperature, long-term weather patterns, atmosphere, the air, the gases, the pressure, etc. Next, let's discuss the scope of meteorology. The scope of meteorology is broad, covering various aspects, such as weather forecasting. In weather forecasting, predicting short-term weather changes to help in planning daily activities and preparing for severe weather events. In these aspects, predicting the weather conditions for a specific time and place, usually over short-term periods like hours, days, and weeks. And when we say the climatology, studying long-term weather patterns and climate change to understand broader atmospheric trends and their impacts. When we say climatology, from the word climate, it is a long-term weather patterns. Next aspect is we have atmospheric science, exploring the physical and chemical processes in the atmosphere, including air pressure, humidity, and temperature dynamics. Atmospheric science is the study of the Earth's atmosphere, including its composition, temperature, humidity, and movement. Next, we have environmental meteorology. Environmental meteorology in this area examines the impacts of weather and climate on the environment. It includes studying air quality, the effects of pollution, and the interactions between the atmosphere and various ecosystems. So environmental meteorology is the study of the impact of weather and climate in the environment, including air and water pollution and the effects of human activities on the atmosphere. Next, we have agricultural meteorology. So what is agricultural meteorology? Agricultural meteorology, this specialized field focuses on the relationship between weather and agricultural practices. It provides farmers with critical information on optimal planting and harvesting times, irrigation needs, and pest control strategies. In this area, agricultural meteorology is the study of the relationship between weather and climate and agricultural production, including the impact of weather on crops, livestock, and soil conditions. Now, let's move on to the importance of meteorology. Meteorology plays a vital role in our daily lives, such as disaster prevention. In disaster prevention, meteorology helps prevent loss of life and property. In this aspect, meteorology helps predict and prepare for natural disasters like hurricanes, floods, and landslides, saving lives and property. Next, we have navigation safety. Navigation safety, accurate forecast ensures safe travel. So in this case, accurate weather forecast ensures safe travel by air, land, and sea, reducing the risk of accidents and delays. Next, we have food security. Weather data optimizes crop yields and weather data helps farmers optimize crop yields, manage irrigation, and prevent crop damage, ensuring a stable food supply. Next, we have resource management. Forecast predict energy demand and optimize supplies. Forecast predict energy demand, helping utilities optimize energy production and reduce waste, ensuring a reliable energy supply. Another importance of meteorology is public health. Weather alerts prevent weather-related illnesses. In public health, weather alerts help prevent heat-related illnesses like hypothermia and other weather-related health issues. Next, we have leisure planning. Forecasts enable planning for outdoor activities. Forecasts enable people to plan outdoor activities, vacations, and events, making the most of their free time. Another importance of meteorology is economic development. Weather data informs business and policy decisions. Weather data informs business decisions such as supply chain management, inventory planning, and risk management, supporting economic growth. Another importance of meteorology is the urban planning. Forecasts help design resilient infrastructure and cities. Meteorologists help identify areas of the city that are prone to heat islands, where built-up areas absorb and retain heat. This information helps urban planners design strategies to mitigate the urban heat island effect. In conclusion, meteorology is a crucial field that impacts our daily lives, economies, and environments. That's all for my discussion about the introduction of meteorology, and the next topic will be discussed by my group mates.
Hi, I'm Marian Acasto from BSEd Science 2, and today we are going to talk about the history of meteorology. Of meteorology, pre-scientific meteorology, ancient times 17th century, observation and interpretation. Early civilizations like pre-classical era, evidence suggests that many ancient civilizations like Mesopotamia, Egypt, China, and India made weather observations for classical agricultural purposes. They developed calendars, noted celestial events, solstices and eclipses, and observed animal behavior to predict seasonal changes and weather patterns. These were largely qualitative observations lacking systematic measurements. Records were often kept in the form of written accounts, drawings, or carvings on stone. In classical era Greece and Rome, Aristotle's Meteorologica stands out as a landmark around 340 before Christ era. While not based on empirical measurements, it specifically described atmospheric phenomena, including the water cycle, clouds, and weather systems. The work was highly influential for centuries, but its reliance on philosophical reasoning rather than scientific observation limited its predictive power. Roman engineers and architects also took note of weather conditions for construction purposes. Medieval period. In Europe, weather forecasting often relied on religious interpretations and folklore. Farmers and sailors developed their own weather wisdom based on experience, passed down through generations. However, systematic scientific progress was slow during this period. In other parts of the world, like China, more sophisticated astronomical observations continued to inform weather predictions. Scientific revolution and the birth of modern meteorology in 17th to 18th centuries. Measurement and instrumentation, the invention of instruments, the 17th century marked a turning point with the invention of key instruments. Barometer Evangelista Torricelli in 1643, measuring atmospheric pressure, revolutionized the understanding of weather patterns or systems. Thermometer, various inventors evolving designs accurate temperature measurement became possible, enabling more precise weather observations. Rain gauge, various designs evolving accuracy, measuring rainfall provided crucial data for hydrological studies and agricultural planning. Early scientific societies, the formation of scientific societies, the Royal Society in England, fostered collaboration and the dissemination of scientific knowledge, leading to more systematic weather observations and data collection. Benjamin Franklin's work on the Gulf Stream and the use of kites to study atmospheric electricity significantly advanced meteorological understanding. He also advocated for a network of weather observers across the American colony. Rise of synoptic meteorology, 19th century, networks and forecasting. Development of weather networks, the 19th century witnessed the establishment of national meteorological services in several countries. Telegraph enabled rapid transmission of weather observations, allowing for the creation of synoptic weather maps, maps showing weather conditions across a wide area at a specific time. Early forecasting techniques. Early attempts at weather forecasting relied on analyzing synoptic weather maps and identifying patterns. This laid the foundation for modern weather prediction. The role of railways. The expanding railway network facilitated the rapid dissemination of weather information, improving the accuracy and timeliness of forecasts. Barometer Evangelista Torricelli in 1643, measuring atmospheric pressure, revolutionized the understanding of weather patterns or systems. Thermometer, various inventors evolving designs accurate temperature measurement became possible, enabling more precise weather observations. Rain gauge, various designs evolving accuracy, measuring rainfall provided crucial data for hydrological studies and agricultural planning. Early scientific societies, the formation of scientific societies, the Royal Society in England, fostered collaboration and the dissemination of scientific knowledge, leading to more systematic weather observations and data collection. Now, the 20th and 21st centuries, the computer age and beyond. Numerical weather predictions, or the NWP, the invention of the computer revolutionized meteorology. NWP uses mathematical models and vast amounts of data to simulate atmospheric processes and predict future weather conditions. The accuracy of forecasts dramatically improved. Radar and satellite technology. Radar provided a way to observe precipitation and other weather phenomena remotely. Weather satellites offered a global perspective, allowing for monitoring of weather systems on a scale never before possible. And also climate science. Meteorology became increasingly intertwined with climate science, using models to understand long-term climate patterns and predict the effects of climate change. Data assimilation, sophisticated techniques for combining observations from various sources like satellites, radar, surface stations into weather models, have further enhanced forecast accuracy. Ensemble forecasting, running multiple weather models with slightly different initial conditions, provides a range of possible future weather outcomes, improving the understanding of forecast uncertainty. High-resolution modeling. Increasing computing power allows for the development of high-resolution models that can capture smaller-scale weather features, improving local forecasts. Meteorology has a profound impact on our lives, influencing decisions in agriculture, transportation, energy production, and disaster preparedness. Accurate weather forecasts are essential for safety and economic well-being. Our accuracy of our weather forecasting is really continually improving. Thank you.
Hi, my name is Christian Joseph Odaigan from BSA Science 2. I'm from Group 1 and my topic is the development of meteorology. The development of meteorology, the study of the atmosphere and weather phenomena, spanned thousands of years and has evolved from ancient weather observation to a sophisticated science supported by technology and computer modeling. Ancient and early theories. Ancient civilization, the Babylonian around 650 BCE, made some of the earliest weather predictions based on cloud patterns and astronomical phenomena. Ancient Greeks, such as Aristotle, wrote about weather in works like Meteorologica circa 340 BCE, providing natural explanation for weather patterns despite the limited scientific understanding of that time. Medieval period. Meteorology progressed slowly with early tools like wind vanes and rain gauge developed in China and the Islamic world. Scholars in this region translated and expanded upon Greek and Roman meteorological theories. This is the example of wind vanes. The wind vanes used for indicating wind direction is the one of the oldest instrument when mounted on the elevated shaft or spire. The vane rotates under the influence of the wind such that its center of the pressure rotates to leeward, and the vane points into the wind. Rain gauge. A rain gauge is an instrument used by meteorologists and hydrologists to gather and measure the amount of liquid precipitation in predefined area over a set period of time. It is used to determine the depth of the precipitation that occurs over a unit area and measure rainfall amount. The scientific revolution. The 17th century saw advance in instrumentation, including the invention of the thermometer by Galileo and the barometer by Evangelista Torricelli. These tools allowed for precise measurement of temperature and atmospheric pressure, which are fundamental to understanding the weather. Galileo barometer, and this is the example of Galileo thermometer or Galilean thermometer is a thermometer made of sealed glass cylinder containing a clear liquid and several glass vessels of varying density. The individual float, rise, or fall in proportion to their respective density and the density of the surrounding liquid as the temperature change. It is named after Galileo Galilei because he discovered the principle on which this thermometer is based, and the density of a liquid changes in proportion to its temperature. This is the example of Evangelista Torricelli barometer. The first mercury-filled glass tube was originally accepted to have been invented in 1643 by Torricelli, which became known as Torricelli's mercury barometer. In this, he produced a vacuum-filled glass tube with mercury, inverting it and then submerging the open end in a vessel of mercury. 18th and 19th century. Meteorology transitioned into more systematic science, with the collection of weather data becoming more widespread. The telegraph in mid-1800s enabled rapid communication of weather observation across large distances, laying the groundwork for the first weather forecasting system. In 1847, the first meteorological organization, the Smithsonian Meteorological Project, was established in the United States to collect and share weather data. The emergence of modern meteorology, 20th century. The early 20th century saw the development of the Norwegian cyclone model by Wilhelm and Jacob Jerknes, which explained the formation and behavior of mid-latitude cyclone. Technology. The introduction of radiosondes balloon-borne instrument in the 1920s provide vertical profiles of temperature, humidity, and wind. World War II. The war accelerated meteorological advancement as accurate weather forecasts became crucial for military operations. Radar was adapted for tracking weather phenomena like thunderstorm and hurricane. Numerical weather prediction. By 1950s, the use of computers enabled the application of the mathematical equation to simulate and predict weather patterns. The satellite era, the mid-20th century onward. The launch of the first weather satellite, TIROS-1, in 1960 revolutionized meteorology. Satellites provide global views of clouds, storm systems, and the temperature patterns, making real-time monitoring of weather systems possible. 21st century and beyond. Modern meteorology relies on high-resolution computer models, global weather observation networks, and advancement in artificial intelligence to improve forecasting accuracy. Climate science has emerged as critical branch of meteorology, silbing sanga, focusing on long-term atmospheric changes and their impact on ecosystem and human society. Meteorology continues to develop, driven by technological innovation, increased understanding of atmospheric process, and the growing need to predict and adapt to extreme weather and climate change. And this is the end. Thank you.
Good day, everyone. Today, I'm going to discuss my assigned topic, which is the atmosphere and its composition, structure, and layers. So, what is atmosphere? The atmosphere is a layer of gases that surrounds the Earth, playing a crucial role in sustaining life by providing oxygen for breathing, regulating temperature through the greenhouse effect, and shielding the planet from harmful ultraviolet radiation. Without the atmosphere, life on Earth will not exist. The atmosphere was one of the factors why Earth supports life. As a living being, we can survive without food for weeks and without water for days. But without the atmosphere, we will not survive even a few minutes. That's why the atmosphere is not just a blanket of air. It is a critical system that supports and sustains all forms of life on Earth. Next is the composition of atmosphere. The Earth atmosphere is made up of nitrogen, oxygen, argon, and trace amounts of other gases. The most abundant gas in atmosphere is nitrogen, making up about 78% of it. The second most abundant gas is oxygen, making up about 21% of the atmosphere. And the third most abundant gas is argon, making up about 0.9% of the atmosphere. And the remaining portion of the atmosphere belongs to trace gases. For example, neon, helium, carbon dioxide, nitrous oxide, methane, and water vapor are some of the major trace gases that make up a small part of the atmosphere. Makes up about 0.1% of the atmosphere. But humans can also cause some trace gases. For example, chlorofluorocarbons has damaged the ozone layer in the North and South Pole. The next is the structure of the atmosphere. Earth's atmosphere has a series of layers, each with its specific traits, namely the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. So the first layer is troposphere. The troposphere is the lowest layer of our atmosphere. Starting at ground level, it extends upward to about 10 kilometers or 6.2 miles or about 33,000 feet above sea level. We humans live in the troposphere. Nearly all weather events like rain, snow, and storms happen in the troposphere. Most clouds appear here mainly because 99% of the water vapor in the atmosphere is found in the troposphere. The next layer is called the stratosphere, located above the troposphere. The stratosphere extends from the top of the troposphere to about 50 kilometers or 31 miles above the ground. The infamous ozone layer is found within the stratosphere, which protects life on Earth by absorbing harmful ultraviolet radiation from the sun. Ozone molecules in this layer absorb high-energy ultraviolet light from the sun, converting the ultraviolet energy into heat. Unlike the troposphere, the stratosphere experiences a temperature increase with altitude due to the absorption of ultraviolet radiation by ozone molecules. The lack of turbulence in the stratosphere makes it ideal for commercial airplanes, typically fly in the lower stratosphere because this less turbulent layer provides a smoother ride. The third layer of the atmosphere is mesosphere. Above the stratosphere is the mesosphere, extending up to approximately 85 kilometers or 53 miles above our planet. Most meteors born up in the mesosphere. The coldest temperatures in Earth's atmosphere, about negative 90 degrees Celsius or negative 130 degrees Fahrenheit, are found near the top of this layer. The air in the mesosphere is far too thin to breathe, with air pressure significantly lower than 1% of sea level pressure. Next is the layer of very rare air above the mesosphere is called the thermosphere. This layer is characterized by extremely high temperatures due to the absorption of high-energy X-rays and ultraviolet radiation from the sun. Although the thermosphere can reach temperatures of hundreds or even thousands of degrees, the air is so thin that it will feel freezing cold to us if we were in the thermosphere. In many ways, the thermosphere is more like outer space than part of the atmosphere. In fact, the approximate boundary between our atmosphere and outer space, known as the Kármán line, is in the thermosphere at an altitude of about 100 kilometers. Also, many satellites orbit Earth within the thermosphere due to its relatively low air resistance at that altitude. The top of the thermosphere, called thermopause, can vary in height depending on solar activity, ranging from 500 to 1,000 kilometers above the Earth's surface. Although some experts consider the thermosphere to be the uppermost layer of our atmosphere, while others consider the exosphere to be the actual final frontier of Earth's gaseous envelope. As you might imagine, the air in the exosphere is very thin, making this layer even more space-like than the thermosphere. The air in the exosphere is incredibly thin, with atoms and molecules so far apart they can travel long distance without colliding. The upper boundary of Earth's exosphere is not precisely defined and can be considered somewhere between 100,000 kilometers or 62,000 miles and 190,000 kilometers or 120,000 miles above the Earth's surface. The latter value is about halfway to the moon. Ionosphere. The ionosphere is not a distinct layer like the troposphere, stratosphere, mesosphere, or thermosphere. Instead, it is a region within parts of the mesosphere and thermosphere where solar radiation creates electrically charged particles called ions, giving it its name and unique properties. The parts of the thermosphere that align with the ionosphere are where auroras, northern and southern lights are visible. And that's all for my discussion. Thank you for your time and attention, and I hope you were able to gain something from it.